Hey guys, my name is Alan Yoon, and this is lab report number 1. The purpose of this lab is observing Newton's second law, or the momentum principle, by comparing data collected from an observed motion and data generated through prediction using a computational model. The physics can be analyzed using Newton's second law. From the basic form F net equals mass times acceleration, we can perform basic rearrangement to derive this new form, where the final velocity equals the initial velocity plus F net over mass times the change in time, which can be used to make predictions about an object's changing velocity. In this case, however, we are observing an object at a constant velocity, so the net force equals 0, and the final velocity will equal the initial velocity. This is my clip for tracker analysis of a basketball rolling across the floor. The clip begins after the initial push of the ball. The clip cuts off the very beginning right here because of the acceleration from the initial push, and the very end because real-world forces of air resistance and friction would cause the ball to slow down. Therefore, we assume that in the short period used for analysis, the velocity is constant. So we begin at frame 20 and end at frame 53, with each frame measuring about 1/30th of a second. The analysis was calibrated using the diameter of the ball, which measures 0.2385 meters as per regulation NBA-sized basketballs. For future reference, the mass is about 1.04 kilograms. The axis is placed so that the origin is on the ball's center of mass at the very beginning and oriented so that the x-axis is parallel to the ground because the ball's motion is also parallel to the ground. There is no change in vertical positioning to be noted. The ball's motion is toward the negative x direction, in this case left. If the axes were flipped so that the ball traveled in the positive x direction, the graph data would simply have a positive slope rather than a negative slope, but the slope's magnitude would have been the same. As we can see, tracker marks the point of the ball in each frame and records all of the data here, which will be used later in comparing the data. Using VIDLE, I created a computational model that uses Newton's second law to predict an object's motion. Data from tracker was used to form the initial parameters of this model. The mass of the ball can be noted in kilograms here. The initial position relative to my axis on tracker is here. The initial velocity calculated from the first 2 data points in tracker is also included here. And the start time begins at 0. The delta t value used later has to be small compared to the length of the frame, so this time interval is set to 0.01 seconds. Using the initial position and velocity, we make a while loop that combines many iterations of the same formula to predict the object's motion. Here, we see Newton's second law, the form that was discussed earlier used for predictions. The ball's changing position with a change in time must also be noted to generate the data to be used later. The while loop is set to stop at 1.1 seconds because that is the length of the tracked clip. We also note a 0 net force in the loop of predictions because we assume the velocity is constant. It is actually possible to note all of the pushes and pulls acting on the ball. Here we see that gravity pushing down and the floor pushing up cancel out to give no net force in the y direction, and forces such as friction and air resistance are assumed to be so small that they can be deemed negligible. Now, with all of the aspects accounted for, we can run the model to generate the prediction that we desire. If we run this program, we see that the displayed visual is similar to the motion of the basketball clip, a ball rolling to the left. Only by analyzing specific data can we notice discrepancies. Here we have the graphs created from the data generated from the observed tracker analysis, noted by the green triangles, and the predicted computational model, noted by the blue diamonds. We see that the data virtually overlaps, so the prediction was relatively accurate. However, this experiment is certainly not ideal since the net force is not actually 0, close but not quite. The computational model ignores the existence of friction and air resistance, so the graph is perfectly straight. The results could be improved if these forces could be measured and included into the model. Although if we think logically, these forces should slow down the ball even if just slightly. My track data actually displays a slightly faster velocity towards the end as seen here. Several possibilities for this error include, but are not limited to, human error in analysis, if I did not cut off enough from the beginning of my video to account for the initial acceleration, or if I was imprecise in my tracking, or a non-level surface on the bathroom floor on which I rolled the ball. In conclusion, while not an ideal experiment, we see how we can apply the physics of Newton's second law to analyze and predict an object's motion at constant velocity. Thank you.